Welcome to this chemistry lecture series. In this video, we're going to look at chapter 8, section 2, which is going to focus on how the position of equilibrium can change. So we talked about equilibrium and what it is, and the fact that it is a reversible reaction that will eventually read as just state, where the forward and reverse reactions are happening at the same rate, and the concentrations of the reactants and products are constant, but that can actually change. Once we have reached equilibrium, the state of equilibrium for a reaction, it does not necessarily mean that the reaction will change like that. Any external changes will affect the equilibrium. So the position of equilibrium, whenever we talk about the position of equilibrium, we are talking about the relative amount of reactants and products. Are there more reactants than products? Are there more products than reactants? By how much? What ratios? That kind of thing. The position of the equilibrium and the relationship between the amount of reactants and products can be shifted. It can be changed when we change a few different factors. We could change the temperature, the concentration, or even the pressure for very specific reactions. So anytime we change one of these external factors, we can, what we call, shift the position of the equilibrium. So like we discussed, equilibrium is when reactants become products and vice versa. It's dynamic. So even once we have reached the equilibrium state, the reactants are becoming products and products are becoming reactants. But because the rates of the forward and reverse reaction are equal to each other, the concentrations of the reactants and products don't change. Now, that is not to say that we couldn't have what we call a product favor equilibrium, one where we have more products than reactants, or a reactant favored equilibrium, one where we have more reactants than products. Now, if we change the temperature, for example, of the reaction or the equilibrium state, or we change the concentration of one of the reactants or products, or even if we change the pressure, we can shift that equilibrium. We say the equilibrium is shifting right when the products increase in comparison to the reactants. So we say the equilibrium is shifting right when the forward reaction starts happening more quickly than the reverse reaction to reach a new equilibrium. So changing temperature concentration could do this, but essentially anytime the forward reaction takes over once we have reached equilibrium state, and products start being made more than reactants, we say that equilibrium is shifting right. On the other hand, the equilibrium shifts left when products decrease in comparison to reactants. When the reverse reaction starts taking over and we make more reactants than products until we reach equilibrium again, we say that equilibrium is shifting left. So different changes in external conditions or even in concentrations can cause an equilibrium to shift right or left. Now, I should say that this change is to reach a new equilibrium state, meaning that the concentration of the reactants and products will change, but it will eventually stabilize and reach a new equilibrium. Now, there are multiple factors that can affect this, but they're all going to be guided by the same principle when it comes to shifting equilibrium, and that is Le Chatelier's principle. Le Chatelier's principle says that if one or more factors that affect equilibrium, i.e. temperature, pressure, or concentration, is changed, the position of the equilibrium is going to shift either left or right in the direction which reduces the change that we have created. So we can tell what effects concentration will have, or temperature will have, or pressure will have on an equilibrium by looking at the stoichiometric equation and the enthalpy changes depending on whether we're looking at concentration, pressure, or temperature. Now, essentially what's going to happen is that, like we discussed earlier, if we have a reaction like this where dinitrogen tetroxide gets converted into nitrogen dioxide, if we start with nothing but N2O4, that N2O4 is going to undergo the forward reaction, create NO2. The concentration of N2O4 is going to slowly start to drop, but eventually it will stabilize. The concentration of NO2 is going to start increasing as the forward reaction gets created, but eventually it will start to stabilize because at this point we have reached equilibrium. So here, from around here to here, we have reached equilibrium 1. Meaning that this reaction is happening, the four reactions happening, the reverse reaction is happening, and as they're both happening, eventually the rate of the forward and the reverse reaction are equal to each other, and the concentrations of N2O4 and NO2 eventually stabilize, becoming constant. So we have reached equilibrium because we have constant concentrations. Well, let's say we made something happen. So here in this dashed line right here, you can see it says change made. So in this particular case, if you look very closely here, you'll notice that we have a spike in the concentration of NO2. So concentration is one of the things that can affect equilibrium. So you'll notice that if we add a bunch of NO2, which is what happened here, we add NO2 and we add N2O4 into here. So we're changing the concentrations of both chemicals. We can see that by that drastic upward spike in the concentration. You see that that change causes then another change in equilibrium. This is where the equilibrium is going to start either shifting left or shifting right. In this particular case, you'll see that the concentration of N2O4 increases while the concentration of NO2 decreases. That's because the equilibrium is now shifting towards the left. Because the concentration of N2O4 is increasing, with that equilibrium shifting left, and eventually what's going to happen is that a new equilibrium is reached. So if you look at right around this point, you'll notice that the concentrations become constant again. That's because we have reached another equilibrium, equilibrium 2. When we talk about Le Chatelier's principle, essentially what we're talking about is reaching an equilibrium and then causing something that changes that equilibrium. Messing with either temperature, pressure, or concentration, in this case concentration, to then make that mixture of reactants and products reach a new equilibrium. Equilibrium is not something that's avoided. Once we change something, either concentration, pressure, or temperature, what we're making the reaction do is reach a brand new equilibrium, but an equilibrium nonetheless. Notice how the concentrations are starting to stabilize. They start to become constant again. Now, this is not going to obviously change the stoichiometry or anything like that. Notice how it's a 1-to-2 ratio in the stoichiometry between N2O4 and NO2, and the changes reflect that. N2O4 concentration changes by X, while NO2 concentration changes by twice the amount from those original, and I say original quotation marks because from those change concentrations. And that's because of the ratio, right? Anytime we break down 1 to N2O4, we make 2 NO2s. In order to make 1 N2O4, we need to use up 2 NO2s. So they're always going to change by a 1-to-2 ratio. But yeah, notice that's what when we talk about Le Chatelier's principle, we're talking about having a reaction that has already reached the equilibrium state and then causing some change that makes it or forces it to reach a new equilibrium state. Now, still equilibrium, still concentrations are still constant, the rates of the forward reverse reaction are still the same, but it is a new equilibrium with different concentrations. And that's because we, in this case, mess with concentration, but we can do it with temperature, we can do it with pressure. And we're going to look at each of these individually. And we're going to look at them all within the scope of Le Chatelier's principle. Le Chatelier's principle says if one or more of these factors is changed, the equilibrium is going to change, so it's going to either shift left or shift right, in order to counteract the change, in order to reduce the change that we have created. So let's look at what that means in each factor here. So let's go concentration first. Le Chatelier's principle is probably the easiest to understand when it comes to concentration. If we add more of a product, then the reaction is no longer at equilibrium and the product will react to give the reactant and readjust the equilibrium. Meaning that if we add more of a product, we're going to shift the equilibrium to use up that product. And out of the two reactions, the one that uses up the product is the reverse reaction. If we add more of a reactant, then the reaction is no longer in equilibrium, and we're going to shift the equilibrium, or nature is going to shift the equilibrium to use up that reactant. Which of the two reactions uses reactants? Well, the forward reaction. And so where the equilibrium is going to shift to the right. So let's look at that here. I'm going to put my work screen up. So essentially what we're saying here is, let's say we have, I'm going to keep it very simple, reactant in equilibrium with products. And this could be any reactant, any product really. We're just doing this for the sake of visualizing the change, right? Le Chatelier's principle says that equilibrium is going to get reestablished by either shifting this left or right to counteract the change. So let's say we come in and we add reactant. If the change in concentration we're making is adding reactant to an equilibrium reaction, a reaction has already reached equilibrium, what's going to happen here is that if we add reactant, according to Le Chatelier's principle, the equilibrium will shift to use that reactant that we added. Well, which reaction here uses reactant? The forward reaction or the reverse reaction? The forward reaction is going to use up that reactant that we added. Because if we undergo the forward reaction takes over, our reactants are used up, products are being made. So the equilibrium is going to shift right if we add reactant. It's going to shift right because that's what's going to use up the reactant according to Le Chatelier's principle. If we instead add product to the equilibrium, so if we add product to this equilibrium, then Le Chatelier's principle says that we want to use up the product. If we increase the concentration of the product, then Le Chatelier's principle says that the reverse reaction is going to take over. Why? The reverse reaction is going to use up the product and make reactants with it. So when we add product to an equilibrium, the equilibrium is going to shift left. Because by shifting left, by the reverse reaction taking over, we can use up the product that we added. And now this actually goes both ways. Why? What happens if instead of adding product, we remove product? If we remove product, if we lower the concentration of a product, then think about it. How does Le Chatelier's principle say that this equilibrium is going to react? If we remove product, then Le Chatelier's principle says that this equilibrium will shift to counteract that change. How do we counteract removing product? We create product. How do we create product? The forward reaction creates product. So removing product causes a reactant to shift right because it creates more of that product. Reversely, same thing with the reactants. If we remove reactant, and if there's multiple reactants, it doesn't matter which one we remove. But if we remove any amount of reactant, we lower the concentration of the reactant, then Le Chatelier's principle says we need to shift this equilibrium to make more of that reactant. Which of the two reactions, forward or reverse, makes more reactant? The reverse reaction. So by removing reactant, the equilibrium is going to shift left to create more of that reactant. So this is the essence of how Le Chatelier's principle works when it comes to concentrations. If we add a certain reactant or a certain product, then the equilibrium is going to shift to use up the reactant or product. So if we add a reactant, equilibrium shifts to the right because the forward reaction uses the reactant. If we add product, equilibrium shifts left because by using the reverse reaction, we can use up that product. And then removing is the same thing, lowering concentration, same thing. If we remove product, then the equilibrium is going to shift to the right because by shifting to the right, the forward reaction will create more of that product. But on the other hand, if we remove reactant, then the equilibrium is going to shift to the left because the reverse reaction will create more of that reactant. So this is how you can view concentration changes when it comes to equilibrium. If we look at this chart, this is an example of just that, of just what we talked about. So if we look at this reaction, and I'm gonna write up here, if we have nitrogen reacting with hydrogen to create, and this is an equilibrium reaction, ammonia, NH3, three hydrogens react with one nitrogen to create two ammonia. Well, if we look at this right here, this reaction is at equilibrium, right? Hydrogen, ammonia, and nitrogen concentrations are constant. But let's say we grab this reaction at equilibrium, this mixture at equilibrium, and we add hydrogen to this mixture. If we add hydrogen to this mixture, we're increasing the concentration of a reactant. Le Chatelier's principle says that in order to counteract that additional hydrogen, the equilibrium is going to shift either left or right to do the exact opposite. So if we're adding hydrogen, we're going to want to use hydrogen, which means the forward reaction will happen. So the equilibrium is going to shift right to use up that hydrogen. And that's exactly what happens. If we look at these, notice how once we add the hydrogen, the concentration of hydrogen starts going down. Why? Because the forward reaction is happening more quickly than the reverse reaction to use up some of the hydrogen. Well, notice also how the concentration of the ammonia, which is the product, is increasing because, again, we're shifting the equilibrium to the right, creating more of that ammonia. And even though we didn't add any nitrogen, notice how the concentration of the nitrogen does also decrease. Very slightly, but it does also decrease. Why? In order for the equilibrium to shift to the right, it needs to react hydrogen with nitrogen. Meaning that as a result of us adding hydrogen, we're also using up some of the nitrogen. So this is what it looks like when the equilibrium is shifting to the right because our concentration spike, because we have added a reactant. The equilibrium is going to shift to the right, use up the reactants, which in this case are hydrogen and nitrogen, and create more of the product, which in this case is ammonia. Eventually, the equilibrium is reestablished. Notice how all of the concentrations do end up becoming constant, but they're not reestablished to the same concentrations. This is a new equilibrium. Notice how in the new equilibrium, the concentration of ammonia is higher than the original equilibrium. Concentration of nitrogen is lower. And the concentration of hydrogen, even though it was used up, is still higher because we added hydrogen to begin with. Also notice by the amount that it changes, right? If we look at the amounts here, and I'm going to use green, the amount of from the time of the change to the new equilibrium, if we look at that change in hydrogen, we look at the exact same change for nitrogen and the exact same change for nitrogen and then his ammonia, notice how nitrogen changes by a much smaller amount than both hydrogen and ammonia, and how hydrogen changes by a bigger factor than ammonia. So why is that the case? Well, again, the coefficient. This is a 1 to 3 to 2 ratio in the coefficients, meaning that the change for hydrogen, once the equilibrium is reestablished, is going to be 3x, 3 times bigger than the nitrogen, which is only when I call it x, because of the 1 to 3 ratio. Meaning that the ratio between nitrogen and ammonia is going to be 1 to 2, so we can call this 2x. So notice how nitrogen changes by the least, whereas hydrogen changes by the most, because of those coefficients. So these are all things to consider whenever we talk about shifting an equilibrium. This equilibrium shifted because of the sudden addition of the hydrogen, which shifted our equilibrium towards the right because of that higher concentration of the reactant. And then, so according to Le Chatelier's principle, we need to shift the equilibrium. Nature, really, not we, is going to shift the equilibrium to the right to use up some of that the added reactant. So this is for concentration. But what happens when we are instead looking at pressure? Now, pressure is very unique. It doesn't affect every single reaction. Pressure will mostly affect only reactions that have gases as reactants or products. Gases, if you remember from our prior conversation in the year, gases create pressure when the particles of a gas bounce around the container, and so they create pressure as they bump into the container walls. Well, because of that, pressure is only significant when it comes to equilibrium if the reaction has a gas in it. So it doesn't need to be all gases, it just needs to have at least one gas as a reactant or a product. An increase in pressure will shift the equilibrium towards whichever side of the equation has the lowest number of gas molecules. This is the important part here for Le Chatelier's principle. An increase in pressure will shift the equilibrium towards whichever side of the equation has the lowest number of gas molecules. Why? Again, Le Chatelier's principle does not change, it's just applied differently. If pressure is created by the molecules of a gas bouncing against the sides of the container, then it stands to reason that if we have more molecules, we're going to have more pressure. On the other hand, if we have a same container, same size container, but we have less molecules, then less pressure is going to be made because the molecules are not as tight in the container, and so pressure is going to drop. So how, according to Le Chatelier's principle, if we need to counteract an increase in pressure, how are we going to do that? We're going to counteract an increase in pressure by lowering the number of gas particles. So whenever a pressure is increased, we're going to shift to the side with the lowest number of gas molecules. Why? Because that will lower the pressure that we just increased. So we got to look at how many gas particles there are in a reaction in order to be able to tell what the pressure will do. It's not like with concentration where like if you increase reactants, it shifts right. If you increase products, it shifts left, and it's always going to be that case. Because some reactions have more gas on the right, on the reactant side than the product side, and other reactions are the exact opposite. So let's look at this reaction, for example, so we can look at what we were discussing. Imagine we have 3 moles of a gas in the reactant. So here we have sulfur dioxide reacting with O2. So in total, we have 1 mole of, let me fix that. We have 1 mole of oxygen and 2 moles of sulfur dioxide, which means we have 3 moles of a gas. On the product side, we have 2 moles of sulfur trioxide. That's the only gas, right? So it's only 2 moles of a gas in the product side. So why these? And this is, this reaction happens to be all gases, but it's because these are the gases. Gas, gas, gas. We will not count it if it was a solid or a liquid or aqueous. That means that if we increase the pressure on this reaction is going to shift from the left to the right. We're going to get a shift to the right in this reaction. Why would that be? If we increase pressure, the only way to counteract that increase in pressure is by lowering the number of particles of a gas so the pressure can go down. If we undergo the forward reaction, we go from 3 moles of a gas to the reactants to 2 moles of a gas in the products, which is going to cause the reaction or the pressure to decrease as we're going from more moles of gas to less moles of gas. On the other hand, if we did the exact opposite, if we decrease the pressure, here, so if we grab the exact same equilibrium, we decrease the pressure, the equilibrium will actually shift to the left. Why? How do we counteract a decrease in pressure? We counteract a decrease in pressure by increasing the number of particles, gas particles, to create more pressure. As we go from 2 moles of a gas in the products to 3 moles of a gas in the reactants, we increase the pressure by creating more gas particles, counteracting that initial decrease in pressure. So the equilibrium is always going to shift. When you increase the pressure, when pressure goes up, equilibrium will always shift from from more gas moles to less gas moles. When we decrease the pressure, we're always going to go from less moles of gas to more moles of gas, because we counteract pressure by creating more gas particles if we want to increase it, so if we want to counteract that drop in pressure, or by creating less gas particles if we want to decrease the pressure, meaning we want to counteract a pressure going up. So I know this can be very confusing when you hear it for the first time, but the more you think about it, the more you kind of practice it, the more clear it's going to become, because it is based on logic, right? It is based on trying to counteract, to oppose the change that we have. All right, so that's effects of pressure, which again only count if you have a gas somewhere. And then we're going to look now at the effects of temperature. Now, temperature is the last one, and temperature is not going to depend on stoichiometry or moles and balancing. It's going to depend on whether the reaction is endo or exothermic. If a reaction is endothermic, if the delta H is positive, then an increase in temperature is going to shift the reaction to the right and vice versa. If the reaction is exothermic, if the delta H is negative, then the increase in temperature is going to shift the reaction to the left and vice versa. So one of the things you have to be aware of is that when you have a reversible reaction, like the reaction we were just looking at, nitrogen reacting with hydrogen to create ammonia, if the forward reaction is exothermic, then the reverse reaction is endothermic. And there's a few ways we can think about this. We can think of it in this manner of opposites. So, like we said, increasing temperature for an endothermic reaction will shift it to the right, decreasing it will shift it to the left, and vice versa for an exothermic reaction. So here, if we have this reaction, this is exothermic, then increasing the temperature on an exothermic reaction shifts the reaction to the left. So this increase in temperature here, because the forward reaction is exothermic, is going to cause a left shift. Whereas decreasing the reaction, because the forward reaction is exothermic, is going to cause a shift to the right. Now, this does depend a lot on you memorizing this. I don't particularly like this explanation. So let me give you the other explanation for this, and which I much prefer and makes it easier to visualize. Let's say you have an exothermic reaction. I'm going to start with exothermic. And again, just to recap a little bit from the chapter 6, remember that the enthalpy change for an exothermic reaction is going to be negative. Oops. So let's say we have an exothermic reaction. We have reactants and products. And again, because we're talking about equilibrium, this is an equilibrium reaction. But one of the things you have to realize is that for an exothermic reaction, a reaction which gives out heat, that means that heat is going to act like a product. Because the exothermic reactions give off heat. They give off energy, meaning that heat is a product. So we could, for an exothermic reaction, view changes in temperature like we view changes in concentration. What does that mean? That means if we increase temperature, what are we doing? If we increase the temperature of any reaction, we're adding heat. We're adding heat to the reaction if we increase the temperature, because by making things hotter, we're adding heat into the mix. Well, if the reaction is exothermic and heat is a product, Le Chatelier's principle says that if we increase the temperature, we're going to want to shift this equilibrium to counteract the change. Well, how do we use up heat? We shift the equilibrium towards the left. So an increase in heat to an exothermic reaction is the same as an increase in the concentration of a product, because exothermic means heat is a product. And so, just like Le Chatelier's principle says, the equilibrium will have to shift to the left, making the reverse reaction happen to use up the extra heat. On the other hand, if we lower the temperature of a reaction, right, that's like removing heat. When we lower the temperature of a reaction, we're removing heat from the reaction. And so we're removing a product. How do we counteract that change? According to Le Chatelier's principle, the equilibrium is going to shift to the right, because by shifting the equilibrium to the right, more heat gets created. And so we counteract the change in lowering the heat. That's an easier way of viewing how temperature is going to affect a reaction based on whether it's endo or exothermic. Now, what about the endothermic reactions? Well, it's the exact opposite. Let's say we have an endothermic reaction. And again, remember, endothermic reactions are ones where delta H is going to be positive. So what if we have an endothermic reaction? How is this any different? Well, for an endothermic reaction, we still have reactants that are going to be in equilibrium with the products, because we're still talking about equilibrium reactions. But the heat in this case, because the reaction is endothermic, it requires energy, is not going to be a product. The heat is going to be a reactant, because the endothermic reaction requires energy in order to occur. And so heat becomes a reactant. The logic, though, is the same. Where the heat is, whether it's a reactant or product, is what changes between an endothermic and an exothermic reaction. But the logic is the same. If we increase the temperature on an endothermic reaction, we're still adding heat, because that's what increasing temperature means. We're adding heat into the mix. Well, if the heat is a reactant for an endothermic reaction, and we add heat by increasing temperature, then the reaction is going to shift, or the equilibrium is going to shift to the right. It's going to create more products, because we're feeding this endothermic reaction heat, which is a reactant. If we instead remove heat by dropping the temperature on an endothermic reaction, we're removing the reactant that it needs to happen, so the reverse reaction will happen. Because how do we counteract a removal heat? We do the reverse reaction for an endothermic reaction, which will create more heat. Because remember, the forward reaction is endothermic, then the reverse reaction is exothermic. When we're talking about an exothermic or endothermic reaction here, we're talking about the forward reaction, being endo or exothermic. So this is a much better way, in my opinion, to think and to visualize how heat is going to affect either an endo or exothermic reaction, and how it will shift its equilibrium. And that's it. That is the last of the factors. That is how temperature affects the equilibrium, how it will shift the equilibrium of a reaction. So that's it. Those are the three factors. Concentration, which is always going to act the same way. Pressure, which is only going to affect reactions which have, and let me actually go back. Pressure, which is only going to affect reactions that have gases in them, and it will depend on which side of the reaction has more or less gas moles. And then temperature, which will affect the reaction in opposite ways, whether it's endo or exothermic. Again, with that being the forward reaction that we're discussing. That is it for section 8.2. I will see you all in the next video for 8.3.